So,
Look at all the melons they have at the fresh time market.
okay, yeah. We have 2 distributors. So, like, distributors bring food to grocery stores, yes? Okay. We have 2 distributors, J and K, and J is organic, okay? And what we've done here is we've said the distribution of the diameters of the melons from distributor J is approximately normal with a mean of 133 and a standard deviation of 5. Everybody with me? Okay. For melons from this distributor, what is the probability that it will have a diameter that is greater than 137 millimeters? Here's what happens for me here. The first thing I want to do is I see approximately normal with a mean of 133 and a standard deviation of 5. Does that feel like a reasonable thing to do so far?
I forgot about that.
And I'm even going to label this with a J because I know that this is from distributor J. How are we feeling so far? All right. And if I want to know what is the probability of greater than 137, and it's been a while, but does anybody remember how we calculate this? This is a normal CDF question. So we would it's happened that kids have forgotten how to do stuff in the calculator every once in a while. Can somebody remind me how I get to normal CDF? Second vars. Option number 2. It's going to ask you for your lower. What's my lower in this case? 137. It's going to ask you for an upper. What's my upper in this case? A gajillion. What's my mu?
133.
That's the mean. The standard deviation is 5. Oof! Did you change your standard deviation to 5?
Why is the standard deviation?
Because
It's right there. It's right there. It is right there.
Yeah. I made the standard deviation. No. That's supposed to be 133, not a million. It's like that. It's supposed to be there.
I'm gonna go and buy all these melons and do a taste test. They're like $1 per melon.
Reverse the order.
okay, so guys, if I say the probability that the diameter is greater than 137, would that make sense in this case? Is equal to 0.2119 is how that would round. If you call that 0.212, I wouldn't care. How are we feeling so far? What a great opportunity to review normal distributions. I don't normally get this excited about normal distributions, but
Did you consider doing stand-up?
I would, but I'm not tall enough.
You want to know who does stand-up?
My stand-up will be more
You
like
want to know who does stand-up?
Carter Black.
He does stand-up?
Yes.
He does do stand-up. He does do stand-up.
Okay, so I'm making a recording of this. Can we stop and be focused? All right, yeah, let's go ahead and read the next part. And then we're going to sit back for a second and reevaluate some of our stuff in the first part. We didn't do anything wrong. I'm going to change some communication a little bit and stuff, okay? All right, so distributor K provides melons from non-organic farms. The probability is blah, 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 blah. The watermelon selected at random will have a diameter greater than 137. So we're talking about this diameter greater than 137 again. Are you guys with me? So I'm going to, instead of calling this, are you guys cool if I start saying, well, what if we started thinking about a probability event G? And G represents a diameter greater than 137. Does that make sense? And because now I have two probabilities associated with this, like, greater than 137. I have the one we found in part A, and I have the one we have in part that was given to us in part B.
I'm sorry, where did we get G?
I just made it up.
Oh.
I'm just creating a new event. So when we look at this, what was this really? It is the probability of G. All I'm saying is that I don't want to keep writing out diameter greater than 137. I'm using G as a shortcut. Okay? But when we think about this, this is that probability given that the melon came from distributor J. Okay? Is everybody with me on that? Okay. So when we get to part B, now I have the symbols in the communication to say, all right, this 0.8413 is the probability of G. Given that it came from distributor K. And I think it's just going to help us keep clear all that, because as you look, we're going to start having lots of probabilities thrown at us, and it's going to be hard to keep them all straight. That's the intention here. Yummy coffee. Okay. What else do we got here? For all the melons at the store, we know that 70% are provided by J and 70% from K, or 30% from K. So if I put a 0.3 and a point, oh boy, that's not right. 0.7 here and a 0.3 here. Would you guys be comfortable with that? All right. So I'm going to be at J, right? If it comes from J, it's either one of those bigger ones or not bigger ones. So if I call this branch G and this branch G complement, would you guys be comfortable with that? Yeah.
So like on a test or for this, for example, if we were to put like for G like less than 130 or diameter is greater than 137 and then diameter is less than 137,
You'd be fine. It's
Okay.
just, you're going to get really irritated with that. Like, the goal is just trying to make things a
Yeah.
little bit easier.
okay, so it's like not graded. It's just to help you.
It's just to help you. Yeah. You wouldn't have to do this. Correct.
Yeah.
That's correct. Okay. What probability should I put right here?
0.2119.
What is the probability of G when I'm on the J branch? It is that 0.2119. Do you want me to zoom in on that? So remember, these two probabilities have to add to 1, right? Okay. All right, what about here? What's the probability it's big if it's coming from distributor K?
0.8413.
0.8413. Leaving this other one to be 0.1587. And then, what are we asked to find here?
I had a question real quick. What is the G complement? Again, what does that mean?
Not G. So that would be the small. If we let G be the big melons,
Yeah.
G complement would be the small melons.
Small, okay.
Okay, what are we asked to find in part B? I guess we didn't really get there yet. Oh, what is the probability that if I randomly pick a melon, it'll be one of the bigger ones? It will be greater than 137. So really, that happens twice, right? That either happens here or here. Those are the ones that end up with a watermelon that's bigger than 137. Does this make sense? Okay, so if I wanted to find the probability of this branch, what do? I multiply. I'm going to do that 0.7 times the 0.2119. And then I'll do the same thing down here. I'm going to do the 0.3 times the 0.8413. So then if I want to find the probability of just one of the bigger watermelons, I'm going to take that 1483 plus the 0.2524. %. How are we feeling about this? Pretty good, decent? Okay. And again, the reason a tree diagram helps is we were given some conditional probabilities, so it kind of helps us see the difference between the J versus G. Okay? Or J versus K. All right. Now, a reminder, I would not expect you to write this part down, but on your formula sheet, you're going to be given that the probability of A given B is equal to the probability of A and B over the probability of B. So this is what you would have on your formula sheet that you would use to refer for this last question, okay? Part C says, given that a randomly selected melon has one of those big diameters, so given G, what is the probability that it came from distributor J? Sorry, thanks for playing. But we're going to use the 0.14. But that 0.14 is that that those two things did happen. I want to say, hey, I got one of these big watermelons. What's the probability it came from J? What you gave me was the probability of J and G. What I need is, what is the probability of J given G? So what we're going to do is basically saying, of all the big watermelons, what's the probability, what percent of them came from J? That's essentially what they're asking us to find. Okay, now, if I wanted to use this formula, I don't know what I'm doing there. But now I kind of want to turn it into a panda face palming. Okay, if I wanted to use this formula in this setting, what would my fraction look like? P of 0.7 plus. P of, just think of it this way, J and G over P of G. Yeah. Okay, now let's think through where this goes, okay?
0.1483 over 0.4006.
J and G happens when I follow the J and G branch, and I end up with that 0.1483. Is everybody with me? Over the probability of G. Well, what's the probability of G? The 0.4007. We found it right here. And I think it works out to be like, I don't know, 37%. Mm-hmm. Not an easy topic. There's a reason we've had multiple examples of this, you guys. This is not easy. This is what we call Bayesian probability after a guy named Bayes. Yes?
So when the like P or J and G, like I see how you like followed kind of like that line. If it was like the or, how you?
Oh. Well, the probability that it came from J or G is 1.
Oh. Okay.
Because that's all of them, right?
Right. Okay.
And when I said on Monday we're going to talk about a quick lesson on something called the addition rule. The addition rule is all about or. Everybody good? All right. So from here, you have several options.